Today, we're tackling a problem that challenges us to identify common elements across multiple collections. Given three distinct arrays of numbers, how can we efficiently pinpoint those values that show up in at least two of them? It's a classic scenario with a clever twist. The task is to find all unique integers that appear in at least 2 out of 3 given integer arrays, nums1, nums2, and nums3. Each array can contain duplicate values, but our final result should only include unique numbers. The numbers themselves are constrained to be between 1 and 100, inclusive. We need to return these qualifying numbers in any order. A straightforward but inefficient approach involves iterating through the first array, and for each number, checking if it exists in either the second or third array. Then, we do the same for the second array against the third, ensuring we don't double count. This would involve nested loops or repeated linear searches. For example, checking nums1 against nums2 and nums3 directly leads to a time complexity of roughly O, n1, n2 plus n1, n3, and then adding O, n2, n3 for the remaining checks. Given array lengths up to 100, this could quickly become O n cubed in the worst case, making it too slow for larger inputs. Space complexity would be OK for the result set. The key insight here leverages the small constraint on the number values. They're all between 1 and 100. This immediately suggests using a frequency array. We'll declare an integer array of size 101, initialized to zeros, to act as our counter. To handle duplicates within each input array efficiently, and ensure we only count a number once per array, we first convert each input array into a hash set. This gives us unique elements from each array in constant time lookup. Then, for each unique number in the first hash set, we increment its corresponding count in our frequency array. We repeat this for the second hash set and then the third. Finally, we iterate through our frequency array from index 1 to 100. Any number whose count is 2 or greater is added to our result list, as it appeared in at least 2 of the original arrays. Let's trace with nums1 equals 1, 1, 3, 2, nums2 equals 2, 3, and nums3, 3. First, we initialize our count array of 101 zeros. We create hash sets. Set 1 equals 123, set 2 equals 23, and set 3 equals 3. Now we populate the count array. For set 1, count becomes 1, count 2 becomes 1, count 3 becomes 1. Next, for set 2, count 2 increments to 2, count 3 increments to 2. Finally, for set 3, count 3 increments to 3. After processing all sets, our count array has count 1 equals 1, count 3 equals 3, and all others are 0. We then iterate from 1 to 100. When I is 1, count is 1, so we skip. When I is 2, count 2 is 2, so we add 2 to our result. When I is 3, count 3 is 3, so we add 3 to our result. The iteration continues, but no other counts meet the criteria. The final result list will contain 2, 3. This is correct because 2 appears in nums1 and nums2, and 3 appears in nums1, nums2, and nums3, thus satisfying the at least 2 condition for both. You'll spot this pattern when you need to count occurrences across multiple collections, and the values are within a small, fixed range. The constraint on value size, typically small integers like 1 to 100 or 0 to 1000, is a strong indicator that a frequency array or fixed-size array can be used for counting instead of a hash map, providing direct indexing. Time complexity is O, n1 plus n2 plus n3, due to iterating through each array once to build the sets, and then iterating through the frequency array. Space complexity is big O of 1, constant time, because the frequency array size is fixed at 101, regardless of input array sizes. This frequency array pattern is incredibly useful. Try the next problem where you might see this same pattern. Don't forget to like and subscribe for more efficient algorithm breakdowns.